Good morning, guys. Welcome back to another episode of Introduction to Computer Networks. This is Polly again, streaming live on NTU. We are now in week 14. This is the Wednesday session. In fact, today there's nothing more to say, except that let's go ahead and start with the topics. We do have quite a bit to go through today. Okay? And the first is to wrap up distance vector routing. Okay, so you see that we'll talk about the bad news travel slow. Yesterday we talked about good news travel fast. And you heard Polly saying that, hey, the convergence time under the good case or no change case is about the diameter of the network. Now, bad news travel slow is a little bit tricky. Okay, in fact, today we're going to go through 3 quizzes, 46 to 48, to make a point that bad news indeed travel really slow sometimes using distance vector. Okay, and that is a major headache. Okay, using distance vector. Oh yeah. Hi Yanjia, Aslam, Tasha, and Pinchang. Okay, good morning to you all. So you can see in the first hour today, it's gonna be very interactive. Polly plays some video and you go on and work on quiz and back and forth. Okay, so that is just to prove bad news travels slow. And then we'll talk about this thing called poison reverse. It is the solution to address this bad news travel slow issue. Okay, and that will conclude distance vector. So the end of the first hour, maybe the beginning of the next hour, will be a summary of the 2 routing principles, LS and DV. Okay, so guys, Polly is gonna do a pop poll again, asking you which one you like better. Okay, so we can compare, right? At the beginning, Polly just overview the 2 routing, right? I ask which one you prefer, isn't it? And many of you find that distance vector very interesting. Less heard of. Now, let's wait until we summarize and compare again the 2 routing principles. And I'll ask you, well, which one you like better. Let's see if there's a change of mind, okay? Good. And yeah, good morning, Zhu Xun. So that will be the first hour. The second hour, guys, okay, the second hour will be very straightforward, and much of the second hour is going to be descriptive, because what we'll be doing is we'll introduce a real internet routing protocol for each of the routing principle. Okay, so there's going to be a few protocols that we run on the internet. Okay, among them, there's one called OSPF that is based on the LS routing principle. Okay, and then there's this very special routing protocol called BGP that runs globally across the internet, and that is based on the DV routing principle. Okay, so second half of the lecture, I'm sorry, it's not going to be very interactive, but Polly is still going to take some pop polls. Okay, good. So that is what's going to happen today. Good. So let's go ahead and start with bad news travel slow, and we'll start from introducing the first quiz today, 46. Okay. So what you're seeing is, hey, let me then go to the whiteboard so I can dribble. So this is the exact network that we've used showing good news travel fast. Okay, and in that scenario, the link cost between X and Y is changed from 4 to 1. That means, oh, link cost reduced. That's good news. Okay, and we've shown that it's going to converge really fast to the optimum route. Okay, in 2 iterations. But now, bad news travel slow. Okay, you see the scenario is different. The link cost between X and Y is changed from 4 to 60. Okay, bad news indeed. All right. So let me go here. So what you'll be asked to do is to do this. Okay, can you calculate Y's distance vector table? Okay, right after the change, meaning time 0. Okay, now this can be a bit challenging for you guys. All right, so what Polly is going to do is to do this. Polly would derive X's table, okay, right after the change. So X is here. Okay, so the other end of the link. Okay, so what I will be doing for X will be very similar to what you do for Y. Okay, so let me play the video deriving x's table right after the change. And so you want to pay attention and see if you can follow suit and derive y's table after the change.
Yeah, quiz 35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that will be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through the first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy came from no y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz, to y. So dz to y. And that is in, distance vector of z came from no z earlier. Z to y, it says 1. So we put 1 here. Okay. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z.
All right, so so in the end we get these 51, 50, okay, for dxy and dxz. So now you derive y's distance vector. That is saying calculate dyx and dyz. All right? Yeah, hi Yuting. So let's go to the score space. Okay, I see some of you have already started typing. Good for you. But guys, the point of the quiz is, once again, for you to exercise, writing the lecture time, so you don't have to study all that much after the class, okay? So please do show the full derivation, okay? Yuan Hao, I can tell you already that this is incorrect, okay? For this quiz, you will see that if you show the full derivation, the result will come up differently than what your intuition suggests, okay? Yuan Hao, okay? So, yeah, I know it's tricky. Guys, you have 10 minutes. Walk this through. So let's start counting time, okay? We will not be taking the fast responders, okay? And even if you make mistakes, as long as you correct them, we'll accept your answer, okay? Polly might give you extra credit for it, all right? So let's learn something, okay? And instead of trying to be correct all the time, instead of trying to be fast all the time, okay? So you might sense that Polly would really like you to go faster, okay, to get things correct. Of course, we all do, okay? But that is under the assumption that you really get the idea, okay? So 10 minutes, take your time. Make sure that you get this right. That way, you don't have to study all that much. And you might get a better score this time for the last exam. See? 10 minutes. It's now 10:30. Let's start counting time. Okay, try to provide your answer by 10:40. All right, I guess, yeah, you guys all got it. Okay, so you see that showing the derivation helps. Okay, in fact, I think Team 7 demonstrated very well. Okay, so Team 7 here, Yuan Hao was originally a little bit mistaken, and Bo Yun is trying to help. Okay, but you see that even though the final answer is incorrect, but I can see in the derivation that you got it. You got it. So in this case, Polly always give points. But when you give just the final answer, it's a little bit hard to tell whether you really get it. Okay. And that explains why Polly prefers that you show derivation. Because after all, the purpose of teaching is so that you learn something. Okay. And by showing derivation, I'm a little bit more sure that you pick things up. Good? Okay, I see. 2 more teams typing things up. Okay, all right, Bo Yun. Okay, good. You know what? You guys are still within the time. All right. So while the other team is typing the answer up, why don't we go on? Okay, continue the quiz series. Okay, and now we'll go on to
dy.
We'll go on to quiz 47. Okay, so we just solved 46. But you know what? Let me do this. Let me play still. Okay, how Polly derives. Okay, let me play still how Polly derives table to y. Okay, and that is going to be in this video. Okay, so guys, if you are still a bit lost, okay, I understand that one of you guys in a team will represent the team and type up the solution. So why don't you, okay, those who don't really understand what's going on, follow this video. This is Polly deriving y's table at t0.
dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful, and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first. And then z says, I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. Okay. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
All right, so that was to show y at t0. Good, we'll move on to quiz 47. You see that after, okay, we develop x's table and y's table at t0, we're going to send that information to know z. So this is what it's going to look like. So you see, this vector is going to be sent, right, according to distance vector, to the neighbors. Okay, and z is a neighbor of x. Similarly, z is a neighbor of y. So you see y's table, the dx will be the new dx coming from no x. dy will be the new dy coming from no y. And with these two vectors received being new, different, what would z do? Z would run the Bellman-4 equation calculation and regenerate dzx and dzy, isn't it? Okay, this is according to the distance vector. So now, follow the Bellman-4 equation, calculate dz and dy. Dzx and dzy. So let's go to the discourse space. Okay, channel 14, quiz 47. Guys, again, the point is that you learn. I understand that some of the teams might be a little bit faster. It's okay. If you want to ensure that you get this right, don't look at their answers yet. Okay, try to work on your own. Okay, that usually will be more effective. Okay, so you guys would have, hey, this time less less than 10 minutes. How about we set it to 8 minutes? Okay, so you guys have 8 minutes, and that's start counting time. It's 10:45. Okay, we'll try to come back to collect you guys' answer. 10:53. right, so I can see that you guys are really picking things up. So Yuting is also getting it. Very good. And we don't need all that much time now. All right. So why don't we go on and play the video demonstrating how Z's table is derived. Okay, and this one is going to be from Polly.
You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2. Right? And at T1, Z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-Ford equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 wings. And therefore, we update dz to 7, 1. Okay. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5, and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finished calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Okay.
Yeah, so hey, let's try to calculate y's table at T2. Okay, and that is equivalent of saying this. So after we recalculate z's table at T1, then we can go on, try to calculate y's table at T2 and know that x vector should be the new x vector, new x vector here. And the z vector should be the new z vector here. Okay, so let's go on and calculate y. So similarly, let's go to the score, channel W14 quiz 40A. Okay, and this time, how about we reduce the time even further? Okay, just 6 minutes. Okay, and 55, 60 minutes means we'll come back to collect answer at 11:01. All right, let's start counting time. All right, guys, you've got it. Okay, and you see what? A rotating pattern, isn't it? From 601, 710, and what? A01. And guess what? In the next moment in time, T3, what would the Z's table be? 910. And then 1001. And this is going to oscillate until finally the real path is discovered. Okay, so let me play this video, okay, which shows how Polly derives Y's table at T2, and Polly is going to explain further how come it takes 44 iterations for bad news to try to finally converge. Okay.
Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x, through neighbor x, neighbor z. Link cost 60, link cost 1, link cost 60, link cost 1. The xx, 0, the zx, look up the table, z's x, 7, 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only $7 to go to x. And this is going to go on, in fact, because y here is going to announce dy also, okay, to all the neighbors. And z is going to recalculate the dz. And guess what? And the next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cause to x. So until, okay, in dz, the value becomes 50, 1, 0. Okay, and how many iterations would that be? Yeah, came all the way from 7 to 50, that will be 43 iteration, okay? And including the initial iteration, that will be what? 44 iteration, okay? Until, okay, z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true.
It is a little bit tricky, isn't it? Distance vector. This is a major issue in distance vector. And to address this issue, we have this thing called poisoned reverse. So this video, less than 2 minutes, explains the idea of poisoned reverse. The problem here is, okay, right after link cost change, when y is trying to recompute, okay, the best route to x to z, okay, particularly to x, Bellman-Ford algorithm says y needs to try, right, calculating the total cost through neighbor x, neighbor z. Through neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, okay, just to get from y to x. So together, total cost 60, okay, not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. Okay, so y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So Z is going to send the packet back to y. And y is going to send it back to z. Z is going to send it back to y. So this packet here is going to loop for a while, okay, until y discover, okay, the real shortest path to x. So z here, okay, being still under the impression that the best route is the one before the link change, okay, needs to know about the link change. Poisson reverse is working this way. This is to help, okay, preventing bad news travel slow. In Poisson reverse, y and x, okay, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite, okay? That way it prevents, okay, y selecting z, okay, as the shortest distance to x. All right, so that's the idea. And let's walk through an example, okay, which is the example we use for quiz 46 to 48, and apply Poisson reverse and how that addresses the bad news and show that how it addresses the bad news travel slow problem.
Let's use the same example to illustrate how Poisson reverse works. taking one step back before we have the link cost change. Now z here will discover a shortest path to x this way, z, y, x. So shortest distance from z to x is 5, and the next hop router is y. Now, link xy here, the cost changes from 4 to 60. X, Y, these two routers being connected to the link will be able to discover the link cost change, but Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay, a funny value for the shortest distance from Y to X, which we see from the network after link cost change, there's no way this is the right value. So to avoid, okay, having confusion such as this, we should stop, okay, Z from keep telling Y this is the shortest distance. So Z tells Y instead, okay, the distance to X is not 5, instead being infinite. Okay. And that is what you're seeing here. Distance from Z to X at Y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. Okay. If this node here discover there's a route coming from the neighbor and using itself as the next hop. Okay. So if Y here discover in one of the neighbor, okay, and this neighbor is using itself, okay, as the next hop to a destination, okay, set this entry here in Y's table to infinite. With now the Zx being changed to infinite, the way we calculate dy in iteration t0 will be different. Okay, so dyx particularly is the entry with different value. It was previously 6. Okay, but now let's see how it's going to look like from y to x. Okay, there are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx, dxx, dzx. Set up table, xx 0, zx infinite. So 0 here, infinite here. Comparing the two, yeah, 60 better. Okay, therefore, shortest distance from y to x is now, yeah, the direct link xy. And then the next point in time in T1, z here is going to receive the distance vector from x and y, and this time the yx is 60. That's going to change, yeah, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1, 50 and 1. The xx and the yx, the xx, the yx. So xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here, from z to x, yeah, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. Okay, and so y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes, 60 and 1 are the link cost. The xx 0, the zx, zx, entry value being 50. So 51 compared to 60, 51 wings. So to go from y to x, now the shortest distance is, yeah, this path. And in fact, at this point in time, so let's update the distance vector for y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
All right, so that was poison reverse and working on the examples we see bad news travel. So you know what? And this is a perfect time to take a break. So let's take 10 minutes break. It's now 11:11. We'll resume at 11:21. right, guys. Yeah, let's come back to the lectures. So, what remains in routing principle is just a summary video. Okay, so you will see Polly comparing the two principles again. And right after this video, Polly is going to take a poll and asking you which one you prefer now. Okay.
Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. dv is the distance vector. Let's compare the message complexity first. If you recall, in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links. Okay, there are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost N E. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. Okay, so overall, the cost can go as high as N cube. So link state message complexity, not good at all. Distance vector, on the other hand, okay, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. Yeah, so in terms of message complexity, dv is slightly better. Now, the second metric, the speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being n squared. There's some optimizations one can apply that takes you to n log n time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state, very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time, is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase that router is malfunctioning, yes, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short cost, short link cost to a particular neighbor, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DV and then pass the incorrect information further. Each node's table is going to be used by the other. Each node's distance vector is going to be used by others. This error is going to propagate out throughout the network, and it might take a long time for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness,
link state here is still, okay, winning by a head, by a neck. All right, so you hear that link state more predictable. Distance vector less predictable. Okay, so here, the poll is between link state and distance vector routing. Which one do you prefer now? Okay. If you have a reason, let us know. Okay, August, standing by your choice. Okay. Still cooler. Yes, Ryan, I agree. Okay. Hey, some of us like movies that are horror, suspense, right? But some of us like comedies, romantic. So, of course, we can all have our own preference. But, August. Yeah, go. By the way, guys, August is trying to help teaching. Because internet in the backbone at the higher level is running distance vector indeed. Okay? Yeah. Link state only runs in a smaller domain. Okay, great. August, thank you for setting the stage for the next videos to come. Okay, so guys, as you can observe, right? Many of you change your mind, right? Previously, when we take the first poll, you preferred DV because it sounds refreshing, new, different, and you would like to know, curiosity maybe. But now you see, in terms of robustness, in case you are managing a network, you'll probably prefer link state, isn't it? Yeah, and that is once again for engineering tasks. Okay, it's more that you have trade-off. There's no one perfect solution. All right, so this is quite different from what you are learning from other courses, right? If you can find an algorithm that reduces the big goal from n squared to n log n, that is the n log n one is absolutely better. Okay, so in engineering, so subjects such as computer networks, such as operating systems, very often you see trade-off. In one case, if you consider this factor, one way is better. If you look at another scenario considering other factors, yeah, the other one will stand out. Okay, so guys, thank you for participating in the poll, and this is a perfect conclusion. Okay, we have two routing principles. They all have their advantages and disadvantages. And August just break open the next topic. Okay, so the real internet. Okay, so for the rest of the lecture today, we'll talk about real routing protocols that's running on the internet. Okay, and in this very first video, what I want to say is this. Hey, when we are learning the routing principles, link state or distance vector, we see a network as a graph, right? And routers in the graph. All routers are treated equal. But you know what? If you draw a graph of all the routers on the internet, can you imagine that? That's going to be a huge graph, right? If you run link state on that, that's not possible. That's why we introduced the distance vector routing, right? But then how do you operate this distance vector on such a large network? That's not going to be plausible either, because we know already this distance vector, bad news travels slow and it's hard to manage. Okay, guys. So the real internet routers are organized. There's a structure and it runs in two levels. At the lower level, we have individual routers, and a few of them network together under the same administration will form a system called the autonomous system. So within that system, these routers will be controlled by the admin of the system itself. Okay, and so the operation is autonomous. Another system, another AS, will run autonomously. Okay, so each system can choose whatever intra-AS. So autonomous system is also called AS, okay, a domain, a subnetwork. So within each AS, one can choose a routing protocol. Okay, so the admin can choose the one that he or she is in favor. Okay, but across ASs, there's going to be another protocol. But in order for all these ASs to internetwork, right, at that level, the higher level, all the ASs will need to run the same routing algorithm. Okay, so that is the general idea of internet routing. So in this video, let me first introduce why there's need of such a two-level hierarchy and introducing the term AS, autonomous system.
Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the OSPF, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, BGP, is then based on the other routing principle, the distance vector routing. Well, to be exact, BGP is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, okay, OSPF is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, okay, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. Okay? So until now, the way we're introducing these routing algorithms is actually very idealized. Okay? Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, there's going to be how many? Yeah, these many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, okay, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not going to work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch. Okay, you don't want to go there. Okay, so even if we use a more scalable routing algorithm, distance vector, okay, consider it working on the internet, not going to scale. Okay, we cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers, okay, nearby belonging to another organization, another system. each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here, they will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, one or two routers and make them the delegate routers. These delegate routers, okay, at the higher level will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all of these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, the backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see two levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems.
All right, now, next video, you will hear Polly explain again. These routers within an AS will run a routing protocol, and that is called the intra-AS routing. And then these delegate routers, okay, now will be called the gateways. These gateway routers from across many ASs will run another routing protocol that's called the inter-AS routing protocol. And now you can probably imagine, okay, the forwarding table inside a router. Okay, there must be entries coming from the intra-AS routing as well as entries coming from the inter-AS routing. Okay, so the routing table, the composition gets complex, having a hierarchy of routing protocols on the internet.
Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border of the AS. These powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. So gateway is what, the doorway. Yeah, the router sitting at the border of these AS connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, of its own AS, and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, running in the backbone of the internet, is called the inter-AS routing. Okay, so that is the routing protocol that's running across the gateway routers. So this is the routing, working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have three ASs, one here, two here, and three here. You see individual routers interconnected within one AS. Okay, so there are three here for AS2 and three more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, but you see 1B and 1C both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these two gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. Okay. And inter-AS routing is running in between. Okay. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have two levels of routing running on the internet. Okay. Now, let me show you an example here. Okay. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, okay, not within the region, right, you need intra-AS routing to find the gateway router. And you also need the gateway router, okay, to find, hey, where's the destination gateway router? Right, so you do need inter-AS routing algorithm telling, okay, each node where to pass data further. Just like you need intra-AS routing there telling you, okay, how to reach another router within the AS. Okay, so forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries, okay, for destinations within the AS, okay, within AS. And inter-AS, okay, determines entry for the external destinations. Okay. To be precise, the inter-AS determines which gateway, okay, which router here you should be passing the data to. Okay. But intra-AS will also be telling 1D here, okay, to go to that particular gateway router, what is the right way? So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS.
All right. Now, last video in this overview set of video is to tell you a little bit more about how inter-AS routing works. So within an AS, intra-AS routing, you can imagine a link state routing algorithm or distance vector routing algorithm. From one node to another node, if it's link state, you have a graph, you compute a route. If it's distance vector, you distribute some vectors around and gradually you find a route. So to send data from a source to a destination within an AS, that is straightforward. Now, but to send data from one AS to another AS, how do we do that, right? How do we do that? This video tells a little bit more how we send data from one AS to another AS. And the key idea is that the destination AS will need to send some information out, telling people that, hey guys, I'm here. Reachability information. And that reachability information gets propagated a little bit like the distance vector around all the ASs on the internet.
To make sure the interplay of the intra-AS and inter-AS routing is more clear, okay, let's take a step back. Okay. Look at AS1 here, 1A, 1B, 1C, and 1D. Okay, so these routers within AS would run the intra-AS routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AS routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A, obviously a gateway router for AS3. But you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, 2B, 2C all have links to outside to other ASs. So they are also gateway routers. So these gateway routers at the higher level will be running the inter-AS routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there is another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. With those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. They do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. Okay. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. Okay. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS? And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS router.
All right, you see that even for an internal router within an AS that are not gateway routers, they will still need to know the AS path in order to pass the packets to the right gateways, and then the gateways can pass the packets further. Okay, we'll definitely hear more about inter-AS routing when we introduce BGP, the inter-AS routing protocol running on the internet. But for now, we play two more videos, but these two videos are all about the intra-AS routing, which is the straightforward one. Okay? And first video is introducing the options. There are actually a variety of these intra-AS routings a network admin can choose from.
The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within an AS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within an AS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution in the 1980s, late 80s. And it's based on this principle, distance vector routing. Okay. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. But this other one, OSPF, short for Open Shortest Path First Routing Protocol, this one on the other hand is very popular. Okay, so Open here stands for open source. Okay, RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, okay, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, okay, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IDRIP, IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, okay, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking, okay. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, okay, in SDN, pretty much are doing what? Generalized forwarding, okay, and allowing the flow table being installed, and that's pretty much all, okay. There's no need of running routing algorithms on individual routers. Okay, so starting from 2016, Cisco stopped maintaining IDRIP because there's really no need, very little need of doing routings inside the router.
All right. So, okay, too fast. So this is poll number 2. Hey, if you pay attention to the video, you would know between RIP, OSPF, and EDRIP, which one is based on the link state routing principle? Okay. Sorry. I guess you gave the answer away. Okay, I'm just gonna guess that everyone will follow suit. But hey, guys, just to make sure that you're still awake. All right. Very good. Very good. And OSPF is the protocol that is used very popularly, okay, for ASs and for intra-AS routing. Okay, so OSPF, make sure that you remember this. O stands for open, and then the rest, shortest path forwarding. All right, therefore, next video. So this video is all about OSPF. What it says is essentially OSPF is based on the shortest path routing algorithm with quite a few extensions. Okay, 2 extensions that I find particularly remarkable are first, hey, the propagation, the flooding of these link state reports can be secure. Okay, and that is something that's very important these days for the internet. Okay, and another extension that the poly finds very useful is, hey, OSPF or link state. If you think about it, it seems to be a flat, right, routing. So given a graph, you find the shortest path. But in OSPF, they actually come up with a structure as well. So you could actually run OSPF intra-sub AS and inter-sub AS. So created another level of hierarchy within an AS. Okay, so this video is a little bit long, 6.5 minutes, because it's not just link state routing, it's link state routing with quite a few extensions.
Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, yeah, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in OSPF message. These OSPF messages are native IP packets, meaning the message itself and then we append the IP packet header, and that's all. Okay. There's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cost of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF, designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, okay, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3. Okay. Inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay, The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at a higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.
All right, now the last video today. Okay, so this is the video introducing BGP. Okay, so BGP, we said that it's based on distance vector, but it's to be more precise, a path vector routing. In distance vector, we only see the destination and the cost to the destination, right? But in path vector, you see the whole path along all these gateway routers to the destination, not just the final destination. Okay, so that thing is called a path vector. Okay, and that is the reachability information being propagated and aggregated along the way from the destination AS to the source AS. Okay, so in this video, okay, you will see BGP being path vector, very similar to distance vector, also runs in endless loops. Okay, if you recall in distance vector, in this endless loop, each iteration consists of 3 steps. First, collect distance vectors from neighbors. Second, apply Bellman-4 computation. Third, if the resulting distance vector for the router is better, propagate it further. Okay. In BGP, this endless loop, okay, each iteration consists of 4 steps. Okay, first, collect the AS path or collect the path vector information from the neighboring ASs. Okay, similar to distance vector. But second, recall on the internet, okay, the internal routers will still need to know the inter-AS routes. So the gateway routers or the BGP routers, after collecting these path vector information, second step is to pass this information further to all the internal routers. Third is then to try to compute a path or derive a path. Okay, and before the last step, passing the path information further, passing the path vector information further. Okay, so you will see it's an endless loop of 4 steps. Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the BGP. Now this is also the routing protocol that runs on all these gateway routers, okay, that are higher in the internet routing hierarchy. OSPF, DRIP, EDRIP, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS what is the entire AS level path, inter-AS level path. So that inter-AS level path will contain all the intermediate aliases, okay, along the way from the source alias to the destination alias. So what's nice about keeping track of the entire alias path is this. The source alias knows by default what is the next hop alias. And by counting the number of aliases along the way, you get a rough sense of the path cost as well. But the downside of tracking the entire path is that the memory requirement is higher. But this is okay, right, at the inter-alias level, because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So path vector is exactly what BGP, this one and only inter-alias routing, is based on. First line, BGP stands for Border Gateway Protocol. And once again, it is the one and only inter-alias routing protocol that's holding the internet backbone together. To be more precise, it allows each alias the following. First, it allows the gateway router there for the alias to receive subnet reachability information from the neighboring aliases. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the alias receive path vector from the neighboring aliases gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination alias. Okay? And there are many of these destination aliases, therefore, we receive the path vector, okay, from the gateway routers of the neighboring aliases. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring aliases. As a result, okay, each of these routers within the alias can calculate what is the best path for a particular destination alias. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the alias. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good alias path is selected for a destination alias, the border router there, okay, then can append, okay, the alias's alias number to the alias path derived, and then further propagate this to the neighboring aliases. Okay, so that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. And of course, okay, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. It will announce itself's existence to the rest of the internet.
All right, and that's all the time we have. So you can imagine next week we'll start from, continuing talking about BGP. All right, good. So that's all the time we have. I say goodbye. See you next week. Okay, bye. And guys, this is the end of the semester. Hang in there. We're almost there. Okay, bye.
Okay, bye.